So we're going to move into a second method for solving systems of equations, and this method is called elimination. So based off of the name, what we're going to do is we're going to eliminate, right, to get rid of one of our variables. That way we're left with just one variable, and again, we're really good at solving equations when there's only one variable. That's what we've practiced all this time. Okay. So in the past, we substituted in place of a variable to get rid of it. Here we're actually going to eliminate it. What we're going to do is we want to make sure that the coefficients of that variable are the same or have opposite signs. So if we want like a +4, -4, right, whatever. What we can do because we can't just change one part of an equation, we can multiply or divide the entire equation on both sides, right, both sides of the equal sign, by an integer. Then we'll have two equations that have something in common. So let's look at an example to kind of get a picture of this. So here I have a 4x plus 2y equals 10, right? That's our first equation in our system. We then have our second equation. That looks like x minus y equals 13. If we want to eliminate y, and it doesn't matter, we can also eliminate x, but let's go through the process of eliminating y. What we want is we want the same coefficient, right? Even ignoring the signs, the same coefficient for both. So what I want this to look like is I want this to become a -2y. And it's already a -y. I want it to be a 2y so that it matches, right, the coefficient in front of the y from the first equation. And we'll see why we want that in a minute here. So to get a 2y, well, everything needs to be twice as big. But I need to take that whole equation, that whole x minus y equals 13, and I want to multiply by 2. Because what's going to happen, right, I'm going to get 2 times x, so I'm going to get a 2x. I'm going to get a 2 times that minus y, I'm going to get a -2y. 2 times 13 means I have equals 26, right? Everything has to double, or else I can't say the left side and the right side are still equal. So now we see that we have a -2y from the second equation and a +2y from the first equation. I'm going to stack these on top of each other. This is going to look really similar to the long addition that we did in elementary school. I have 4x plus 2y equals 10. And then right below it, I'm going to write our new equation. I'm going to write 2x minus 2y equals 26. And then what I want to do is, again, just like what we've done in the past, I'm going to do addition here. Because what's going to happen is the 2y, right, looking in the middle row here, when I have 2y and I subtract 2y, I get, well, a 0y. But again, I can't just do that with my y's, so I'm going to do all the other columns as well. On the left side, I have 4x plus 2x. Right? I'm not trying to get rid of every variable at once. I was only trying to eliminate y. So it's okay that I get a positive 6y. And then on the other side of the equal sign, we're going to keep everything where it was. The x's and the y's on the left side, the constants on the right side. When I do 10 plus 26, I'm going to get a 36. All right, so what this equation really looks like now is I have a 6x plus 0y, right? This term is effectively non-existent. I have no y's. I don't even need to talk about the y's because I have none of them. Equals 36. Now I have an equation that I can solve, right? I can find the x value. I can divide both sides by 6, and I get that x equals 6, right? 36 divided by 6. So what we've done now is we found the first part of our solution. Now things are going to be just like substitution. Right? Same thing as we've done before. My solution is made up of two parts. It's made up of an x value and a y value. So I'm going to plug my solved value of x back into either equation. Again, I have my choice. It's going to give me the same result regardless, because again, we're talking about where are these two things equal, right? Where are these two equations the same? So let's go back to the list. Again, it's going back all the way to the top. I want to go not just to any of the values that I've rearranged or multiplied or changed. I want to go, whoops, all the way back up to these equations here, right? What I started with, what the question gave me, again, in case I made any mistakes. And let's choose the bottom one. It looks nicer. Maybe we'll do both again. And let's choose the bottom one. It looks a little nicer, right? Less coefficients, less math for us to do. So we had x minus y equals 13. But we also knew that x was equal to 6. So I'm going to say that 6 minus y equals 13, right? Based off of our solution from the last step. I'm substituting in place of x with that value I know it has. Well, 6 minus y equals 13. Right? I'm going to move the 6 to the other side, minus 6 from both sides. Let's do that in red so we can tell the difference. I have a minus y equals 7. Right? If I divide both of those sides by -1 to get rid of that coefficient, right? That's like a -1 coefficient in front of y. I get -7 for y. It also wants us to verify really quick. So again, we know what that means. Make sure that this solution that we think we have, right, this 6 for x, 7 for y, satisfies both of our original equations. So we had x minus y equals 13. We also had 4x plus 2y equals 10. And we're substituting in the fact that x should be 6 and y should be -7. So let's go ahead and plug those in, right? Let's start on the left side. Again, the x gets replaced with a +6. The y gets replaced with a -7. Nothing else changes. No other operations or constants should change. I have 6 plus 7, right? I have a subtraction of a negative number. Those cancel each other out, right? It becomes a +7. And again, I'm just simplifying the left side, simplifying the right side. I get 13 equals 13, right? That's a true statement. The left side is equal to the right side. Right? It satisfied that first equation. That just means that that's a point, right, that satisfies that relation. Looking at the equation on the right, I had 4x plus 2y equals 10. And again, I'm only replacing the x and the y, nothing around them, right? The coefficients are staying there. This time x and y had coefficients, so they're going to stay exactly the way they are. I had 4 x's, now I have 4 6's. I had 2 y's, now I have 2 7's. So multiplying those in, right, combining those coefficients, I get 24. Oops, and I had a minus sign there. 2 times -7 is -14 equals 10. Right, and this is a great way to check your mistakes. So there I almost kept it as +7. That would have given me some nonsense that says that 38 is equal to 10. Right, but because I noticed my error, I quickly fixed that. Right. 24 minus 14, 10. Is that equal to 10? It is. Right? Therefore, we can finally say our solution is 6, -7, right? We were for sure verified that that is our solution, right? It satisfied both equations. That is the location where these two equations are the same, right? Where their graphs intersect, the x and y that satisfies both equations simultaneously. So let's try some more elimination here. All right, so looking at this first one, right, I have my two equations, I have my two systems. And I want to figure out, right, I want to eliminate one of these variables. So now instead of isolating a variable, right, like we did for substitution, I want to decide what variable to get rid of. Easiest thing for us, really, really similar to substitution. I want to find, usually, if I have anything without a coefficient, that's going to make my life easiest. Because I know to turn y from that second equation, right, into the 4y that we see in the first equation, I can multiply everything here by 4. And that's going to get me that equal coefficient, right? Or equal but opposite. The signs can be different. We'll also see what happens when the signs are the same. But that's going to be our easiest route, right? There's lots of options. I can affect both equations, right? I can affect the first, the second. I can multiply everything if I want. But here we're just going to make that whole second equation 4 times bigger. So what I'm going to get is 4x times 4. I have 16x plus 4 times y, right? That was our whole goal, equals 20 when I multiply to the 5 on the end there. I'm going to do the same thing. I'm going to stack my other equation, this time underneath it, just because of how I've written it. Minus 4y equals 7. And I'm going to do some addition here. Right, going down each of the columns. So the first column, 16x plus 2x, I get an 18x. The second column here, adding plus 4y to minus 4y, right? This is going to be the same thing as before. This turns into a 0, right? A 0y. And then on the right-hand side, on the right side of the equal sign, 20 plus 7, I get a 27. So my equation looks like 18x equals 27. I can solve for x by dividing both sides by 18. Right, get rid of the 18 there, get rid of a factor of 18 there. Right, and this gives me 3 halves, or this gives me 1.5. But again, that's not our full solution, that's the x value. We want to substitute that back in. So again, picking either of our equations, whichever one you'd rather work with, let's plug it into the first one just for the sake of something different. I just want to make sure that 2x plus 4y, or sorry, minus y, right, we're going to use our known minus 4y, should equal to 7. And in place of x, right, my x value is 1.5. That was the solution I got from that last step. So 2 times 1.5 gives me 3, right? I have 2 1.5s. Minus 4y equals 7. My goal is to solve for y here. So I bring the 3 to the other side. I get minus 4y equals 4. Divide both sides by negative 4. And y is negative 1. So that gives us a solution here of 1.5, negative 1. Right, everything after that first step here, this box right here, this is the only new thing for this method. Beyond that, right, we're doing the same thing as before. We find the value of one variable, we plug it back into one of the original equations to find the value of the second, right? You always need both parts for your solution. So let's see what happens in this second one. So here, 2x plus y equals 20, 6x minus 5y equals 12. Now let's do something a little bit different. Say I wanted to eliminate the x's, just for the sake of it, right? I can eliminate whichever variable I decide I think is easier. So for this one, if I want to eliminate the x's, essentially I'm looking for the least common multiple between two numbers. If we go back to the first example, right, the least common multiple between my coefficients of y the least common multiple between 1 and -4, or 1 and 4. Okay, the smallest thing they both multiply to is 4. Here, if I wanted to worry about the x's, the least common multiple of 2 and 6 is 6. So that's the easiest thing for me to get them to look like. Okay? And the easiest way to turn that 2 into a 6 is to multiply everything in that top equation by 3. Right? Then 3 times 2x gives me that 6x. So let's go through that, right? Distribute, multiply everything in this first equation by 3. I get a 6x. Not a 3x, sorry, that's just a multiplication sign. Let me rewrite that so we're clear. 3 times. So we get 6x plus 3y equals 60, right? Everything is 3 times as large. That means that the left side and the right side are still equal because we did one thing to the left that we did to the right as well. If I stack that with my next equation, 6x minus 5y equals 12. Well, before we do anything here, if I add this time, 6x plus 6x gives me 12x. So when the signs are the same, we're going to do the exact same setup we did before. We're just going to subtract everything in the second equation from the first. So before we did some addition, right, because the positive 4, right, and the negative 4 canceled each other out with addition. Here, because our signs are exactly the same, those x's are going to cancel each other out with subtraction. Right, I have 6 x's. I need to lose 6 x's in order for them to be eliminated, right, to disappear. So 6 minus 6, I get 0x squared, right? That was my goal. We want to be careful with our signs here. 3, right? 3 minus 5, or sorry, minus negative 5. Right? Because I'm subtracting, but there's still a negative in front of that 5. I actually am getting a positive 8. So this is where we want to be a little bit careful. 8y. And then 60 minus positive 12, right? That gives me 48. So when we subtract, things are a little trickier, right? Subtraction's always a little trickier because we have to worry about double negatives, but it can be done. If you would have preferred to just multiply this whole thing by -3 and then added, that's an option too. We'll keep going ahead. 8y equals 48. When I divide both sides by 8, right, that tells me that I get a value of 6. And this time I found y first. Again, it doesn't matter which variable we eliminate. We can eliminate x, we can eliminate y, whichever one you decide is easier. Here, again, it might have been easier to multiply everything by 5 right from the start to eliminate those y's. Just want to give you a bit of variation. So I'm plugging that y value back in. Let's go with that first equation, 2x plus y, which is a value of 6 now, equals 20. If I bring that 6 to the other side, 2x is 14. And we get an x value of 7 here. So 7 for x, 6 for y. That's our solution for that second example. So looking at the third question, right, again, we're trying to get one coefficient to match another. If I'm looking at this, to make 5 and 4 look like the same, their least common multiple, right? That's what we're really looking at. We're looking at the least common multiples. So the least common multiple of 5 and 4 is 20, right? That's neither of the existing coefficients. I would have to multiply both equations by some constant, right, some integer, to get them to look the same, right? There's no way for 4 to look like 5 unless I'm multiplying by some ugly decimal value, and that's never going to be fun to work with. If I look at my y's, of 3 and 6, right? Then the least common multiple there is 6, because 3 can turn into a 6 pretty easily. But 4 can't really turn into a 5, and 5 can't really turn into a 4. So here, same idea, ideally getting rid of those y's. And so here, just like our last situation, we're going to take that whole top equation and multiply by 2, right? That's going to turn our -3 into a -6. So distributing that, 5x times 2, I get a 10x. Minus 3y times 2, I get a -6y. 18 times 2, I get a 36. Right, taking my second equation there, I had a 4x minus 6y equals 18, right? I don't want to change that one at all. We got those common coefficients of 6 in front of y. Now, same thing that happened in the last expression, the last system is going to happen here. If I take a -6y and I add another -6y, right, I'm at a -12y. So because their signs are the same, right, for the same sign, we want to use subtraction. Right? That's going to get those signs to cancel each other out. Right? If I have a -6 and then I subtract another -6, that double negative means I'm adding 6. That balances out to a 0 pair. That gets me up to 0 y's. But I want to make sure I'm subtracting everything. So I'm going to do 10x minus 4x. I'm left with 6x. I get -6y. I subtract -6y. Right? Those double negatives, this negative here counteracts this negative here, right? It becomes a +6y. And then on the other side of the equal sign, 36 minus 18, I'm left with 18, right? You just want to make sure you're consistent. If you've decided to subtract, you're subtracting every single term. So moving in to the next step, right, where I solve for x, 6x equals 18, means that when I divide both sides by 6, I get an x value of 3. That's half of my solution. Now I want to sub that in. Again, I can choose either equation from the top, but going back to my originals, not the ones I've manipulated. Let's do 4x. So 4x minus 6y equals 18. So I do 4 times 3. Right? 12 minus 6y is 18. Bring the 12 to the other side, right? Subtract 12 from both sides. Minus 6y is equal to 6. Divide both sides by that -6 coefficient we have left. And it looks like y is -1. So 3, -1 is our solution for that one. So let's move into some of those examples at the bottom. All right, so the fourth question here, 6x plus 6y equals -6. 5x plus y equals -13. Right, pause and give this one a try if you want. The first thing I notice here is, hey, this would be really easy to turn that second y into a 6y. Right, but let's try something new. If you really prefer the addition method, right, where the signs are opposite, if subtracting negatives is not your biggest strong suit, here's what we can do. We can take this whole equation and we can multiply by -6. Right? That way I'm going to end up with a -6y. Those signs will be opposite. They'll be the same size, right? They'll be the same value, the same numerical value, right? Just opposite signs. So what do we get there? We get 5x. When I multiply that by -6, right, I'm getting a -30x. When I have y and I multiply it by -6, I get a -6y. And that -13 when I go ahead and multiply negative 13 by 6, I get negative 13 times negative 6, I actually get a positive 78. Now I'll stack that other equation, right, the one that I didn't alter, I'll put it underneath. 6x plus 6y equals minus 6. Right? Because we're seeing these opposite signs here, the addition is what's going to undo those two, right? Negative 6 plus positive 6. When I'm doing addition, those two cancel each other out. But I need to make sure I add everything else. So I have negative 30, but I gain 6 x's. I'm up to negative 24x. I get a 0y, right? Double check that one. If you're really not sure, plug it into a calculator. Do negative 6. Right, we can even pull this one up here. Do negative 6 plus 6. Oops. Make sure it gives you 0. And then when I do negative 78 plus 6, or sorry, 78 plus negative 6, right, it's like subtracting 6, I get a 72. So, negative 24x, that y term has been eliminated, that's gone. Lets me find out that I have an x value of negative 3. Then, plugging that into one of our equations, let's just go with the one I can see. Again, before I manipulated it, it looked like a 5x plus y equals negative 13. I know the x, right? That was the value I found before. Now I'm going to find the related y. So negative 15 plus y equals negative 13. When I add 15 to both sides, it looks like I get a positive 2 for y. So negative 3, positive 2 is my solution for that one. Let's give the last two a try. Those are going to be our trick questions again, kind of like the last time. Let's see what happens there. So the first thing I notice about this one is I don't have the same things in the same places, right? My terms are kind of jumbled around. I have my y's, yeah, that's fine. But notice that one constant's on the left side of the equation, and in the other one, the constant's on the right side. And in that top one, same idea, my x term is on the right side, but over here, my x term's on the left side. One of the key things about lining them up for doing that addition or subtraction is that all the terms have to be in the same spots, right? It has to be consistent between the first and the second equation. So the first thing I might even consider doing before I multiply by any constants, things like that, I might rearrange this first equation to look like the format we're used to. I'm going to bring the 4 to the right side, and at the same time, I'm going to bring the 3x to the left side. All right, it's going to give me some equation that looks like y minus 3x equals minus 4. Right, so now I haven't changed the equation. I haven't even multiplied by anything. I've just written it so that the y's and the x's and the constants, if we notice here, right, everything lines up. As I look in a row, right, in a column, even my equal sign lines up, and everything's on the left side that's on the left side, and on the right side that's on the right side in both equations. So that's our first super important step. If it doesn't already look like that, we need to jumble some things around so that it's constant between the two. Now, I want to figure out how to get those matching coefficients. Here I'm seeing this 2y and this y. Let's just make that whole second equation 2 times bigger. So I'm going to get a 2y, a minus 6x, and a minus 8, right, when I multiply everything here by 2. Then just stacking that with my second equation, which looked like a 2y minus 6x equals minus 8, and something's looking a little weird here, but let's keep going. Then I want to subtract because my signs are the same, right? To cancel out that 2y and the other 2y, I need to subtract one from the other. So all I get is 0y. And I get a 0x. Weird. Right? It's negative 6y. I actually gain 6y back. Negative 8 plus 8. Well, I get a 0 again. So if we remember, right, when I end up with my two sides, I have nothing left on the left side, nothing left on the right side. When I end up with my two sides that give me a statement that is true, 0 is equal to 0. Right? Or this time we can clearly see my two equations are exactly the same. If we remember, that means I have an infinite number of solutions. Right, and that's what it's going to look like in elimination. Everything is going to eliminate, even if you didn't intend to, right? You just said, I wanted to get rid of the y's. Turns out that everything is equal, right? Everything matches, so everything eliminates. Looking at the last one, I'm sure you can guess how many solutions this is going to have since we haven't seen this type of example, but let's get into it. Right, I'm looking at this one. I'm saying I think if I made everything in the top there 3 times bigger, right, to get that equal y. And honestly, y is going to be the easiest one a lot of the time, especially because we're used to slope-intercept form where the y is already isolated. But we can always do x, right? We just don't want to make sure we're getting rid of constants, because that's not going to help us eliminate a variable. So everything gets 3 times bigger. I get a minus 6x. I get a plus 3y. And I get a 15. Right, looking at these two equations I want to add, right? We see those opposite signs. We know that addition will cancel them out. 6x plus a negative 6x leads me to 0. And then I look negative 3y plus 3y. That also leads me to 0. Then at the end there, I have a minus 9 plus 15. Well, that gives me a positive 6. And I'm going to ask you a question, is 0 equal to 6? Well, no, that's ridiculous, right? 0, 0, 6 is 6. So I end up eliminating both variables, but it gives me a statement that is false. If we remember, right, all that tells us is that we have no solutions. Right, these are two parallel lines, but they have different y-intercepts, right? Their constant values are different. So that's the comparison of those two odd situations, just like we saw in the last, in solving by substitution. So hopefully that makes some sense. Hopefully that's clear for you there. If you have any questions, feel free to send me an email, drop by your tutorial. We have one last topic. We're going to look at some more of those application problems, and then we'll be wrapping up systems of linear equations.